Welcome to topic 1.2. In this topic, I will cover the pressure enthalpy diagram, which is actually a chart that you can visualize how the properties of refrigerant change, okay, in a vapor compression cycle, as well as learning by using the chart, right, we are going to learn how to calculate the amount of heat it absorbed, the amount of heat it rejected, and the amount of work need to be done for this cycle to be completed. So first, okay, before I go into the pressure enthalpy diagram, you need to know what is the definition of enthalpy. Okay, so this enthalpy, right, in a thermodynamic system is a very common parameter. Basically, it tells you the amount of heat content inside a gas, okay, inside a thermodynamic system. So when we say that this particular gas at this state has a very high enthalpy, it means that it contains a lot of heat energy. So actually the units for enthalpy is in kilojoules, just like the units for energy. Okay, but when we are using the enthalpy diagram, usually you will learn this term called the specific enthalpy. So what is the difference? Okay, what is the difference between enthalpy and specific enthalpy? Whenever you see the word specific, it refers to per unit mass. Per unit mass. So when we say it's a specific enthalpy, it means the amount of heat energy it has, okay, per kg, per unit mass. Just like your specific heat capacity of certain material is kilojoules per kg Kelvin. So whenever you see the word specific, it means per unit mass. But however, enthalpy alone, right, don't really tell you much information. What you need to know is the difference in enthalpy. So you need to calculate when a gas exists at a certain state, when you do something to it. So let's say this one is the initial state, and you do something to this volume of gas. Okay, maybe you start to heat it up, or you start to compress the gas, and it will affect the enthalpy value. So this is the final state. So initially, there's an enthalpy value. We call it H1. Okay, after you do something to it, maybe you heat it up or you compress the gas, there is a change in enthalpy. So this change in enthalpy will tell you, okay, whether there is a gain in heat energy or a loss in heat energy. So if this value is positive, okay, let's say plus 30 kilojoules per kg, it means it has gained energy. So most likely you have heated up the gas, okay, and if there's a loss in heat energy, let's say you heated up the surrounding but itself it loses energy, your delta H will be negative. So the difference in enthalpy will tell you more, okay, will give you more information. So now let's go to the pressure enthalpy diagram. Okay, so as the name suggests, pressure enthalpy diagram means your y-axis, okay, your y-axis is actually pressure in terms of kilopascal and megapascal, and your x-axis is specific enthalpy in terms of kilojoules per kg. So that's why this is called a pressure enthalpy diagram. So you notice that there are a lot of lines inside this diagram. Okay, you have this line, and you have a line something like this, okay, that is inside this diagram. So what are all these? Okay, before I go into the details, okay, let me briefly explain what each region actually represent. First, if you look at the top left-hand corner, okay, which is over here, okay, the top left-hand corner, that means before the curved line, okay, before the curved line at the left-hand side, this point, right, this part of the chart, it represents the liquid state. Liquid state. That is to say, if you have a refrigerant having a certain pressure and certain temperature, and if you plot that point, right, it is at this region, it exists as a liquid. Just like H2O at 30 degrees Celsius at atmospheric pressure, it exists as a liquid. Okay, the water that we know. Okay, if this is liquid state, you can guess that at the right hand side, okay, the red color box at the right hand side, your gas, okay, your gas actually exists as a vapor. Okay, so at the right hand side, it exists as a vapor, and they are all bounded by this line. Okay, so for the liquid state, it is bounded by the saturated liquid line, whereas for the vapor state, it is bounded by the saturated vapor line. Okay, so that's to say, at any point, okay, where your refrigerant exists at the right hand side of the saturated vapor line, it exists as a vapor. Okay, so just like H2O in 110 degrees Celsius atmospheric pressure, it exists as steam. Okay, it is a vapor. So if left hand side is liquid, right hand side is vapor, how about the middle part? Okay, this portion over here. How about this portion over here? If the refrigerant, okay, it is at this, is inside this curve, it actually exists as a mixture, liquid plus vapor state. So that is why over here you will notice that there's this percentage. Over here there's this percentage. So if the percentage is, it represents the percentage of vapor inside this mixture. So let's say it lies on the 40% line. It means there is 40% vapor, 60% liquid. Whereas if it's at the saturated vapor line, it means 100% vapor, 0% liquid. So that's the meaning. Okay, how about the blue line? Okay, if you notice there's all this blue line. The blue line represents constant temperature line. Constant temperature line. That is to say, any point that lie along this line, okay, let's look at the top line, okay. Any point that lie along this line has a temperature of 80 degrees Celsius, okay. Whereas the following line, okay, any point that lie along this particular line, it will be 60 degrees Celsius. So if you want somewhere in between, such as 70 degrees Celsius, you need to do interpolation. That means it's in between 60 and 80, it will be your 70 degrees Celsius line. Last but not least, like I mentioned before, the percentage actually tells you the percentage of gas, or in there's a term we call it the quality of the mixture. Okay, so all in all, the pH diagram, okay, you will need to understand what it represents. So any gas, okay, it will be at, you will have a certain point, okay, it will be located at a certain point inside this pH diagram. Okay, so for this pH diagram, right, it is actually for R134A refrigerant. So this particular pH diagram can only be used for R134A. So the real thing for R134A pH diagram actually looks like this. It's very, very complicated. There are a lot of lines, but of course it's more accurate. Okay, that means a temperature line, they break it into a smaller division, okay, and it's much more accurate. Okay, actually, like I mentioned before, just now that pH diagram is for R134A. How about other kind of fluid, such as water? So different fluid has a different pH diagram because the enthalpy value will be different, the constant temperature line will be different, but the general shape will all be quite similar. Okay, that means there's a curved part, okay, there's this curved part over here, okay, and there's all these lines that represent the constant temperature line. So this particular chart that you see over here is for water. Okay, so for water, as we know, we are quite familiar with the properties of water. What do you notice? At atmospheric pressure, okay, your atmospheric pressure is actually 101 kilopascal or 1 bar. You will notice that what is the boiling point? What is the boiling point? So boiling occurs in between the saturated liquid line and saturated vapor line. You will notice that the temperature is a horizontal line. That means during this part, there is no change in temperature. The temperature remains at 100 degrees Celsius, which is what we know. We know that water actually boils at 100 degrees Celsius. But what happens if, for example, let's say we go for mountain climbing and you move up the altitude, you will notice that what happened to the boiling point. Okay, if let's say you want to boil some water over the fire, you will notice that the water boils very fast. But the thing is, the water is not that hot. You will notice that somehow your rice cannot be cooked and the water is not hot. That is because the higher you go, the lower is your pressure. Okay, the higher is your altitude, your pressure will reduce. Okay, your atmospheric pressure will reduce. When your atmospheric pressure reduces, let's say to 50 kilopascal, what happened? You will notice that the boiling point now drop into this line over here. And what is the temperature over here? It is actually below 100. It is maybe around 80 degrees Celsius. So your boiling point will also be reduced. And that is to say, pressure and boiling point is actually interrelated. So the lower the pressure, the lower is your boiling point. So that's the working principle behind a pressure cooker, where we try to increase the pressure such that your water will not boil at 100, it will boil maybe at 120 degrees, and your things start to cook faster. Okay? So, what do we need the pH diagram for? What can it tell us? Okay, we can actually calculate the amount of energy we need in order to convert water, for example, water at a certain condition into steam at another condition. So let's use an example. If we want to know, right, water from liquid at 10 degrees Celsius, okay, how much energy we must put in, okay, we must put into the system such that it will become steam, okay, it will become steam at 200 degrees Celsius, okay. So over this process, right, what happened? Okay, what actually happened in between these two states? So let's analyze using a pH diagram. First, at 10 degrees Celsius atmospheric pressure, the water actually exists at this point. Okay, at the left hand side, the dot at the left hand side. Okay, so at this point, that is your liquid at 10 degrees Celsius atmospheric pressure. So what happened? At 10 degrees Celsius water, okay, you start to heat it up. Okay, you start to heat up the water. What will happen? Slowly, temperature will start to increase and it become 100 degrees Celsius water. So when you heat up, okay, from 10 to 10 degrees Celsius, temperature will increase. Okay, so it is represented by this pink color line over here. So temperature will move, increase to 40 degrees Celsius, to 60, 80, and finally it reaches the saturation vapor line. Okay, sorry, saturation liquid line. So at saturation liquid line is actually at 100 degrees Celsius. Okay. What if you continue to heat the water? Okay, so if let's say you don't stop at 100 degrees Celsius water, you continue to introduce some more heat, it will slowly be converted to steam. So it will become 100 degrees Celsius steam. But of course this process is very long. So initially it's 100% liquid. When you heat it, it becomes 90% liquid, 10% vapor. Okay, and you heat it up some more, it becomes 80% liquid, 20% vapor. And you do that, okay, for a very long time. That is the boiling process. So all the energy that goes into the water at this point will be used to break up your H2O molecule. So your H2O molecule initially is very closely packed together, okay, because of hydrogen bonding. But because you go and heat up, okay, you are heating up the water, it breaks up this bond, hydrogen bond, and it becomes a H2O molecule, and it floats around, so it exists as a vapor. Finally, let's say all the H2O molecule become vapor state. Okay, that means at the third dot over here, it means that all your liquid has actually already boiled off. Everything is become steam, okay, become a vapor. But you don't stop here. Let's say you manage to capture all the steam and you continue to heat it up. You continue to heat up the steam, what will happen? So temperature will start to increase again, and let's say it increase to 200 degrees Celsius before you stop this whole process. So this whole process can be represented by these three different lines. Okay, the pink color line over here, okay, and the orange color line, that is the boiling process, and finally the short blue color line that's over here. So if we want to know how much energy we really need, okay, for this whole process to take place, remember what we are interested in is always the change in enthalpy, delta H. So what do we need to know? We need to know the initial state, initial enthalpy, let's call it H1, and the final enthalpy at 200 degrees Celsius steam, we call it H2. So what is the value of H1? If you look from the look at the pH diagram, okay, at this first dot, you draw a line downwards, okay, you will notice that, okay, the enthalpy is actually very low. Maybe it's around, you cannot really give a very accurate number, but it's around 50 kilojoules per kg. Okay, and you start to heat up, enthalpy start to increase down the line until it is at the very last dot over here. Okay, the very last dot, and you try to read off what is the enthalpy value over here. So the enthalpy value over here is maybe around 2,800. Okay, 2,800 kilojoules per kg. So you have your H1, you have your H2. What is delta H? So very simple. Delta H is simply the difference between these two values, which is equal to 2800 minus 50. It will give you 2750 kilojoules per kg. Okay, so if you refer back to the previous slide, they ask, what if there's 2 kg of water? In this setup, there's 2 kg of water. So what do you need to do? So the amount of energy required for this process to take place is actually equal to delta H multiplied by the mass multiplied by delta H. That is 2 kg multiplied by 2750. So kilojoules per kg multiplied by 2 kg, it will give you kilojoules. So with that, you should get 5,500 kilojoules. So that's how you use a pH diagram for calculation. So that's a very simple example, but we are not really interested in the water pH diagram. We are more interested in the refrigerant pH diagram because that's what we use for the vapor compression cycle.